We've been talking about solutions quite a bit. You should be comfortable with the different ways in which concentration are expressed. We're going to switch gears a little bit here and talk about solubility. We went over the solubility rules the other day. You don't need to memorize them. You just need to be able to apply them. For example, all group 1 containing salts are soluble in water, such as potassium chloride, sodium chlorate, cesium fluoride, etc. What we're going to talk about here is solubility, that is the amount of substance that's needed to make a saturated solution at a specific temperature. What's a saturated solution?
It's like the maximum amount of liquid or like water or something.
The maximum amount of water?
I don't know, but when powder is saturated, it rains.
It can't dissolve.
Because they can't hold anymore, right?
Yeah.
Perfect. All right. So when something's saturated, it holds as much as it possibly can. Think about a sponge. When a sponge is saturated, it's not going to absorb any more water. When you wring out the sponge, is it saturated or unsaturated? Unsaturated, because it can. Think about fats, unsaturated versus saturated fats. Saturated fats have the maximum number of hydrogen they can, and as a result, they're going to have single bonds between their carbon atoms.
Is that better for you?
Which is better for you, saturated or unsaturated? Unsaturated, because you can add things to them to saturate out rather than starting saturated initially. So in regard to solubility, you can use your solubility rules to determine if a solution is soluble. And we want to categorize solutions as saturated or unsaturated. And as you alluded to, a saturated solution can't dissolve more solute at a given temperature, where an unsaturated solution can. Let's take a look at this pictorially so you get a feel. So initially all of the solute can dissolve in the water. You're still unsaturated at this point because you haven't dissolved as much solute as the solution can. Once maximum solubility is reached, the solution will be saturated. And now you'll see some solute settling out on the bottom because the solution's already saturated. There was a slightly better video. The link looks broken. Hang on.
Hi, welcome to a tutorial on solutions, unsaturated, saturated, and supersaturated. How do I tell them apart? Here we have an unsaturated solution. Our unsaturated solution is capable of dissolving more solute. You can keep adding solute to this, and it's still got the ability to make that solute dissolve. In an unsaturated solution, all the solute that's in there is dissolved. That means what? That means no choice, no grit in the bottom. Every single piece of solute in that unsaturated solution is dissolved. Here we have a saturated solution. It cannot dissolve any more solute. But how does a saturated solution look? Well, here's the weird part. In a saturated solution, all the solute is dissolved, which means it looks the same as the saturated, right at the point of saturation. Where the saturated solution is going to look different is when we add more solute to it. If we add more solute to a saturated solution, this will result in undissolved particles. In other other words, we'll have chunks in the solution or we'll have grit at the bottom. That's where a saturated solution begins to look different from an unsaturated solution. Okay, so let's check our understanding. Okay, so here's a quick rundown. In an unsaturated solution, it can dissolve more solute, so when you add solute, it doesn't change the appearance up to the point of saturation. It may look cloudy for a while, but if you keep stirring, it's going to all dissolve. In a saturated solution, you cannot dissolve any more solute. Therefore, when you add solute, it's going to change the appearance. You'll see chunks or grit. Now, no matter how long you stir a saturated solution, if you don't change the temperature, those chunks or grit are not going to go away. One more way to tell you've got a saturated solution. You've reached the saturation point. Supersaturation, oh no, one more term. Let's look carefully at what supersaturation really means. Let's say that I have a solution.
I'm going to walk you through this piece. Let's say you have a solution that's saturated at 10 degrees Celsius. You increase the temperature and you're able to dissolve more solute. Then you lower the temperature and that solute stays in solution. However, if you put a seed crystal in, you'll see what happens. And that's the video I want to show you. This one you'll find. Cool?
Okay. Just really quick, and I add one tiny seed crystal. I'm not sure what it's going to tip of that speed.
So he's got a sodium acetate solution.
It's so cool. No, but it's so cool.
Super saturated state. To a saturated state in just a few seconds. Isn't that cool? So we see that the sodium and acetate ion
And that's the same way you would make rock candy.
Is it a solid now?
It will be, yeah.
Super saturated, saturated.
We'll come back to it.
Yes.
All right. So supersaturated is when the solution contains more solute than a saturated solution can normally hold, and that's because you heated it up, you dissolve more, you cool it, and it stays in solution. But with that seed crystal, you can get the crystals to precipitate out in that cascading display, and one of the best examples is rock candy. We want to look at the factors that affect solubility. There are two factors we're going to look at, temperature and pressure. And to simplify it before we get into the complex graphical analysis, we want to do the following. I'm going to show you a solubility curve. And the first one we're going to look at is a solid dissolved in water, and that water's in the liquid state, and as a result my solution will be a liquid. I'm going to plot temperature in degrees Celsius on the X, and on the Y-axis I'm going to plot solubility, that is the mass of solute in grams over 100 grams of water, that is the mass of the solvent in grams. In 100 grams, actually. Now, different solutes show different solubility curves. I'm going to use a generic one, and this is what you're going to be doing in the laboratory, the second lab of the two. For example, you might get a curve such as that. This curve shows that as the temperature increases, the solubility does what? Increases as well. So anywhere you're on the line, you've got a saturated solution. The maximum amount of solute that can dissolve at a specified temperature. So for example, let's say this is 10, 20, I'm labeling above because I didn't leave enough room, 30, 40, 50, and let's say we've got 10, 20, 30, 40, 50, 60, etc. Anywhere below the curve will be unsaturated. And what do you think will be above the curve? Supersaturated. On the line is going to be saturated. For example, at 20 degrees Celsius, what mass of this solute can dissolve in 100 grams of water? About 23 grams of solute per 100 grams of water. If 23 grams of solute can dissolve in 100 grams of water, how much solute can dissolve in 200 grams of water? 46. Good. If I say to you, you're at 40 degrees Celsius, what mass of solute can dissolve in 100 grams of water? 40. What mass of solute can dissolve in 50 grams of water? 20. Good. If I say to you, at 30 degrees Celsius, only 20 grams of solute dissolves in 100 grams of water, is your solution unsaturated, saturated, or supersaturated?
Unsaturated.
So you see how to read the curves, and you'll get more practice with this when we do the second lab of the chapter. Yes.
Does supersaturated work with like anything?
No. Only certain solutes have the ability to form supersaturated solutions.
I'm confused how you're describing the y-axis. Like, it says solubility, but like I don't understand.
It's solubility, but it's how much solute, so whatever you're dissolving, per 100 grams of water. So when you do your lab, your solute is going to be potassium nitrate because it shows a great increase in solubility with an increase in temperature. So what we're going to do is we're going to solubilize different amounts of it, and then we're going to cool it, and when those crystals appear, we're going to note the temperature, and you're going to generate a curve.
So like, how do you find the solubility?
You will,
Like in a lab?
you'll know how much you added. So for example, in the lab, you'll be adding 2 grams of potassium nitrate per 5 mils of water, because water has a density at least liquid water, has a density of 1 gram per mil. If you're using 5 mils of water, that's the same as 5 grams of water. So you'll know how much you added, and you'll measure the temperature when it's no longer in solution. So if you did 2 grams per 5 grams, and you wanted to know how much potassium nitrate per 100 grams, what would you multiply the 2 by? Not 100. 5 goes into 100 how many times?
I'm just really confused. Oh, I thought you were cross multiplying. Never mind.
Well, you could, actually.
That's what I was doing. That's why I said 100.
Well, 5 goes into 100 how many times?
40.
Times 2 is? 40. And that's how you determine your y-axis points. Your x-axis points you're going to measure in the lab, and that'll become clearer as you go. All right? So that's a solid dissolved in a liquid. Most solids show increasing solubility. We can look at some different solutes in the following panel. One of the reasons that you wash your hands with warm water or hot water is that soap, a solid, dissolves better in hot water than cold water. It barely dissolves in cold water at all. So you wash your hands in warm water so you can get the soap to go into solution so it can react with the grime, dirt, and grease, whatever's on your hand to get it off. And what?
Tea.
Tea?
Yeah, so you help keep the water up.
Yeah, same thing, exactly. Whoopsie. Got carried away. The following is the solubility curve, and this solubility curve is similar to what I drew for you. Here's your solubility on the y-axis and your temperature on the x-axis. What's the difference between the blue and the pink lines? One's showing increasing solubility, the pink is showing decreasing solubility with increasing temperature. Sulfates are a little unusual in that they show decreasing solubility with increasing temperature. The salts you can see otherwise show increasing solubility with increasing temperature. Sugar, is that covalent or ionic? It's covalent, all nonmetals, right? That goes back to the project you did the first semester. If we look here, at 40 degrees Celsius, how much potassium nitrate at 40 degrees Celsius will dissolve in 100 grams of water? About 70 grams per 100 grams of water. At 80 degrees Celsius, how much potassium nitrate will dissolve in 100 grams of water? About 170. So how much would dissolve in 200 grams of water? 340. If you were looking at potassium chloride shown here, and you dissolved 100 grams of potassium chloride at 40 degrees Celsius, would that solution be super, or just saturated? Super saturated, because you'd be above its line. All right, so those are the types of questions that you can ask and that you will see in your classwork. Whereas solids show an increased solubility with an increased temperature in most cases, gases show this. So this would be a gas dissolved in water. So gases show decreasing solubility with increasing temperature. How come you don't turn up the temperature on your fish tank? Why? Why will the poor little fishies go belly up?
Because oxygen.
Because what?
Oxygen.
Go bait.
Because
Like in a microwave?
what happens to the solubility of oxygen gas at higher temperature? It goes down. So there's not enough dissolved oxygen in there, and your fish suffocates. Why do some people have tremendous difficulty breathing on very warm days? Because there's less oxygen because its solubility decreases.
So much sense.
Why does your soda become flat at warm temperatures? Because the carbon dioxide comes out of solution. Good.
Is that why, like, sometimes if you have, like, a fountain drink and then it warms up, there's, like, bubbles on the top?
And why are the bubbles on the top?
So they're less dense and less heat, apparently.
So, how come?
So they rise above.
Because it becomes super saturated.
As you increase the temperature, what happens to the volume of a gas?
Goes down.
It goes up. As the volume gets bigger and bigger, the bubble's going to pop, and the solubility decreases.
I got her on the test.
I got that right.
I got a 96. Excuse yourself.
Yeah. Say it. We all got so.
The following solubility curve shows decreasing solubility of different gases with an increase in temperature. So you see a very different type of graph with gases dissolved in water as opposed to solids dissolved in water. The last thing we want to mention is the effect of pressure. Let's refocus, please.
He keeps touching me.
Dean, please change your seat. And please keep your hands to yourselves. The other factor that affects solubility is pressure. So we have temperature as one factor, pressure as a second. Pressure will only affect gas solubility. You will see that gas solubility increases as the pressure increases. Soda is capped or canned under very high pressure. That's to keep the gases in solution. When you open the soda can, uncap the soda bottle, the pressure will decrease and you will hear that fizzing sound. Some of the gases are escaping from the solution. When you decrease the pressure, the volume's going to increase, those bubbles are going to move upward, and ultimately they will pop. Say it again. Oh, okay. So the solubility of a gas is going to increase when the pressure increases. In that case, the volume will be smaller. The gas bubbles, if you will stay in solution, and your soda will taste better, but I don't recommend soda for children. It's not nutritious. Soda, we'll talk more about soda in our acid-base unit, and you'll see just how acidic soda is and what it can do to someone's teeth, not to mention their digestive system. In any event, in regard to solubility, what are the two factors that affect solubility? Temperature and pressure. Say it again. No gas laws again until the semester exam.
Oh, that's a thing I forgot.
Wait, what is that?
Your goals today are as follows. Understand how to read the solubility curve. In regard to your quiz, which will be Wednesday for all classes, you need to be able to apply your solubility rules. They will be given to you. You need to know how to calculate different units of concentration, including molarity, molality, mole fraction, and dilution. You should understand how to make a solution 2 ways, and you should be able to read solubility curves. In regard to your relevant classwork for the quiz, and this will be quiz 3-5, although it will probably go into the 4th 9 weeks. In regard to your classwork, you should be able to do through 14, and you should be able to do part 1 and part 2 of the second classwork that you received previously. You have quite a bit of time to get your classwork done. Please make it productive time. Questions? Part 1 and 2.